This is a short technical video on how we manage variable reproductive success in males when they're competing with each other. So now I'm going to address a key issue with this type of technology, and that is that males get different number of females mated and there's different male reproductive success. So let's look at a few data sets. I've got a sheep data set and 3 beef data sets from Alison van Eeneren, who's done some work with her colleagues in this area. And here's an example where there are 13 males in sheep, and this is the percentage success, this percentage number of progeny which has been achieved by each of these males. Similarly, for 3 beef cattle data sets, we have values here, and this is 18, 22 and 24 sires used in this example. And Sarah Fagian has kindly furnished us with a data set from Gilthead Sebring, and there are 29 males involved here. Now these numbers of males are probably larger than you might be used to in breeding operations. This might tend to be focused a bit more on production systems. However, you will see that this doesn't matter too much, I think. If we look at what we managed to predict up here, this is a prediction of the percentage of matings are going to get for the rankings of the different males according to the number of males. So if we have 6 males, there's a prediction here running from 40% down to 2%, and that's according to a certain fit that I'm going to make. So first of all, let's see how we model this. Now I did look at a bunch of different Poisson distributions and others, but I've resorted to the good old normal distribution. So the example here is if we have 6 males, what we want to end up with in the bottom line, it's the same figures that you looked at in that spreadsheet, is a percentage going from 40, 24, down to 2.3% is what we might think is typical, if we get the fit right, for the distribution of success in a particular example. And you choose the parameters. The parameters are actually 2 and 3.5 for this. So how do I do that? Well, first of all, for the 6 individuals from selection intensities, we get the number of standard deviation units deviation that we would predict for those 6. Then we add to those to set that the minimum is equal to a certain value, in this case is 2. So the differences between these are just the same as in the line above. And if we make 2 a big number, like 100, that means that the merit for this thing is going to be having relatively little distribution. So if we set the minimum to 102, this would be 104 down to 102. So setting this value low is going to give us a more extreme distribution. Then we take that to a power. In this case, it's the power 3.5, which is actually the best fitting we have. And we simply scale that to a percentage scale to get those numbers here. So that's the simple model that we use. And then we can fit that to those data. If you look at the graphs, here are the sheep, the 3 beef examples and the fish example. I'll move over a bit so you can see that as well. And the blue lines are the observed data, and the orange or red lines are the fit that we get. And so if I look at this minimum power here, so as I said, if you make this a big number, let's make that number 9 instead of 2. And run it, then we'll see that we get a much more even distribution. There's our distribution for 6. And those 2 values for parameters are enough to populate this whole area so that any number of sires will be ranked according to those numbers. And it seems to be quite robust against numbers in terms of its functionality. If I click optimize, then there's our 2 and 3.5. There's the fit, and you can see we get quite a good fit, except for beef here. In this example for beef 3, here it is here, the percentage of matings achieved by the top few bulls is very similar to each other, and that may not be highly typical. What we can do with this spreadsheet, of course, is I could increase the emphasis on beef. Let's increase it dramatically. And when we do that, we get quite different parameters, but a good fit for beef at expensive fit for everything else. We will have a version of this spreadsheet available that you can put your own data into it, make a fit, and find out what parameters are appropriate for you. So I think you'll agree that across these different species and different numbers of sires, we get a reasonably good fit, with the exception of what I mentioned here. And you see the values are very close to 2 and 3.5, which is what we adopt as defaults at the moment in MateSel. So now we go and look at what we do with that information. What we're interested in here is the effect of that uneven reproductive success on males on the coancestries that we get. So this is a very simple example. We're just looking at the male side of things here, a group of 5 males and a group of 6 males. And from the previous spreadsheet with those values, these are the predicted success rates for the top ranked to bottom ranked male in each group. And if we had no relationships, which we have at the moment because NRM is the identity, then you'll see from another video that x prime ax over 2 coancestry, well, the a is identity, so it's just the sum of squares. And so the coancestry is very simply calculated for the simple condition of having even or equal contribution from those males. Now the most extreme, one male, the top male, got all the matings for that group, then the coancestry goes up substantially. But what we're looking at is a distribution. Here it is here, that's the example contribution, having taken account of the fact that there are multiple groups and also 2 sexes. Then we end up with the sum of squares for contributions, leading us to coancestry here. And this is a more generalized version down here with the numerator relationship matrix being taken into account fully. And you can see that the coancestries, which are in row 15 here, are equal down here for a complete consideration of the numerator relationship matrix. But what we can do, of course, is put in some values for the relationships that you get within groups. Any old value is going to do me here. And we've got inbreeding coefficients potentially as well. So I'll say 0.1 and 0.15 here, and run that. And then we can calculate using x prime ax what the coancestry is, and there it is. But importantly here, we don't want to have to do that in MateSel and go and recalculate coancestries. So we've got a method of predicting the extra amount of coancestry you get. Here it is here and here for those 2 scenarios. And when we add them to the even distribution result, we get exactly the same as if we'd done a complete calculation across the NRM. So I'll show you how that works. Here it is here. With a little page of genetic algebra, you come at the end of that to see that this is the component of coancestry that is inflated by the uneven reproductive success in the males. Here it is. And that's a function of the sum of squares of contributions within groups. So I won't go into detail on this. You can have a look at it later if you want. However, there is a component for this where you have even contributions, so you've got to calculate that as well. And the difference between the 2 of them is the extra amount of coancestry you're going to get because of the fact that you've got this increased sum of squares of contributions within groups. So we add that excess and we get the result, as you see here. That's us coming to the end of the video. If you want to make a fit with your own data, you'll find facility to do that in the Excel file MMG parameters that comes with the software download. Thank you for watching.